Um, hello everyone. My name is Fo. My name is Fo. At first, I would like to thank SOFA organization to accept for me to give a presentation today. My presentation topics is towards simulation and design, optimization of underwater and uniform movement case of subaquatic eel. And this is the collaborative work between Soft Haptic Lab and the fraud team in India. And my presentation today includes 5 parts. And in the first part, I would like to introduce about our research objective. In nature, an eel can have an uniform movement thanks to the interaction between its body with surrounding fluid environment. And inspired by this swimming mechanism, we designed a soft robotic which can swim underwater. And this robot is expected to generate a friendly interaction with its surrounding environment, such as in human instincting. However, the design of this robot is not optimized yet. So we aim to input this design to simulate in so far for getting the outcome of swimming velocity, interactive force, and step motion of the Eel Robot. And from this outcome, we want to validate the result by the experiment of this robot and get the optimization in the future. And now we build an analytical model for swimming mechanics of the eel. On the side view, the lift force balanced with the gravity force, and on the top views, the force acting on the eel robot is the total of the thrust and the reaction force, and the total force acting on the eel robot is the total of thrust, lift, reaction, and gravity force. For the detail of the swimming mechanics on top view, when it boy on the eel body moves, the surrounding fluid environment acting exerts on a reaction force Fr on this point, and by projecting the reaction force Fr on the swimming direction or x-axis, we get the thrust force Ft in this function, and the force Ft push the eel to move forward, and when the eel move forward, the fluid generate the thrust force restricts the eel from movement, and the thrust force is the total of the pressure and skin friction thrust force. On the side views, because the gravity force already exists on the sofa, so we calculate the lift force, and in this scenario, the lift force include 2 cases. For case 1, when the eels move with a high velocity in a slope angle alpha, so the hydrodynamic lift is calculated in this function. And when the eels move in horizontal direction with a small velocity, so the lift force can be calculated in the hydrostatic case or buoyancy force in this function. after determining all components of the force. So we get the total force F, the velocity, the body velocity, and the swimming velocity of the eel. And these kinetic characteristics are applied to modeling sub-eel-like robots in SOFA simulation. And the Eel Robot, the Eel Robot has 4 connected links actuated by pneumatic signal. And here, each link consists of a bear, a symmetrical bear of pneumatic structure fixed on a backbone. The skin and the backbone of the Eel Robot were respectively made from the silicone rubber and the plastic. The CAD model of the Eel Robot in the previous slide was made in 3 layers, corresponding with 3 different force fields: fluid pressure, tetrahedron, FEM force field, and the air pressure. And because the air pressure and the tetra force field already given in SOFA, we aim to find the fluid pressure or the water force field acting on the outer skin of the robot. For each node of triangle T, we add the thrust force and the lift force on it, and the force for one node in one triangle T is 1/3 of the total thrust and lift force in one triangle. Because the structure of eel-like robot is very complicated with a large number of elements, so it is very difficult to get a fast simulation in SOFA. In this scenario, we use a beam adapter embedded on the center of the eel-like robot for getting a fast simulation. And this is a similar preliminary result of simulation. We use for the first trial test, we use sweeper with a same dimension with the eel-like robot for simulation. And here the eel can swim in the water, and also the gradient color, so the water force field acting on the eel body. And this is the experiment. We use it for validating the swimming velocity, thrust force, and shape motion of the eel-like robot. And we aim to finish our simulation in SOFA for using this model to get the validation. And because this is the preliminary work, and we have a lot of things to do in the future, that's control the robots model by using pneumatic actuation, simulate with accuracy model for the outcome of the and compare with the experiment, validate, continue to validate the simulation for get a better correction. And finally, we concern the dynamics of fluid under moving impact of the eel. And because we also try to improve our work. So we aim to we want to receive more comment from SOFA community. So if you have any question or any comments, so please contact please discuss with me or contact with the author by this email. Thank you very much for listening.
Thank you very much, Van Pho. They were really right in time for the presentation. Perfect. Is there any questions? So in the chat first, for the moment, I see people typing, but do not hesitate, as I said, to as Guillaume said, to unmute yourself and ask directly the question if you'd like to Van Pho. So Pho, you've got a first question. Can we have some references? So is there some I guess it's also, so is there some work that you're based on, or some other papers that you could that you yourself wrote in the past that you could give as a reference?
So you mean reference from analytical model, right?
I think it's paper, yeah, either analytical models or papers that you would have already written on the topic. Yeah,
where in this research I got some reference, many reference from the hydrodynamics and and some some mathematical from the Eel Robot. Some of them I got from Hill research, and yeah, Hill research. Some of them.
Okay, thank you. Shantanu, do not hesitate to or either write directly in the private chat as well to Van. And again, there will be specific rooms later on dedicated for talking directly to the speakers. In that case, with Van directly. Thank you very much, Van. So it's already